weakly supervised video anomaly detection has a critical blind spot. Most state-of-the-art methods can tell you when an anomaly occurs, but they fail to tell you where. In real-world deployment, knowing the timestamp isn't enough. You need to know if the anomaly is a person, a fire, or a vehicle, and exactly where it is in the frame. Without spatial localization, these systems lack interpretability and are prone to background bias, where the model flags normal activity simply because it occurs in a context associated with anomalies. Today, we're breaking down a new paper from the University of South Florida that addresses this gap head-on. They introduce a patch-based spatiotemporal framework for weakly supervised anomaly detection that jointly learns where and when anomalies occur, using only video-level labels. No bounding box supervision is required during training. The core contribution is a reformulation of multiple instance learning at the patch level, combined with a novel proximity-aware top K selection strategy. The results are substantial, outperforming existing methods across multiple benchmarks, and the authors have released frame-level bounding box annotations for 2 major datasets, filling a massive gap in the literature. Let's dive into the technical details. The problem with existing weakly supervised methods is that they operate at the clip or snippet level. They produce a single anomaly score per temporal unit. This limits their ability to capture localized abnormal patterns. If an anomaly is spatially confined, a global snippet score dilutes the signal with irrelevant background information. To solve this, the proposed method operates on grid-level patch features. The input video is partitioned into non-overlapping temporal segments, each containing 16 consecutive frames. The video tensor is processed through a pre-trained uniformer backbone to extract patch-level spatiotemporal representations. The spatial granularity is defined by a 7x7 grid, resulting in 49 patches per segment. This provides a fine-grained representation without the computational overhead of per-pixel analysis. The architecture processes these features through 2 complementary transformer encoders. First, a temporal transformer aggregates features along the temporal dimension for each spatial patch. This captures motion dynamics and temporal dependencies within each patch location. The features are then reshaped and pass through a spatial transformer encoder, which models relationships among patches within each segment. This allows the network to understand spatial context and how local patches relate to the global scene structure. The output features feed into 2 branches. A coarse-grained branch produces segment-level anomaly scores by pooling across the spatial dimension. A fine-grained branch produces patch-level anomaly probabilities for every patch in every segment. Now here is where the method diverges significantly from standard MIL approaches. Standard MIL typically selects the top K instances with the highest individual anomaly scores to compute the bag score. This is noisy. It can select disjoint snippets that happen to have high scores due to background clutter, rather than the actual anomaly. The authors propose a proximity-aware top K spatiotemporal selection strategy. This is motivated by the observation that anomalous events typically occur over temporally contiguous intervals. During training, the model performs a sliding window selection over the segment-level scores with a window length K for each candidate window. It computes a cumulative score by summing the segment scores within the window. The optimal window is the one with the maximum cumulative score. This enforces a temporal continuity prior, ensuring the model focuses on coherent anomaly segments rather than scattered high-scoring noise. Once the optimal temporal window is selected, the method drills down spatially. For each of the K selected segments, it slides a convolutional window of size ZXZ over the 7x7 patch grid. It computes the summed response for each spatial location and selects the ZXZ block with a maximum sum. This identifies the most discriminative spatial region within the anomaly segment. The selected patches form the positive instance set for the fine-grained MIL objective. For normal videos, all patches are treated as negative instances. The loss function is multifaceted. It uses binary cross-entropy for both the temporal segments and the selected spatial patches. To encourage compact anomaly regions and suppress noise, the authors introduce 2 regularization terms. An L1 norm sparsity loss is applied to the anomalous set to encourage the model to focus on a compact region of patches. An L2 norm consistency loss is applied to the normal set to ensure all patch scores remain close to 0, preventing false positives from background biases. The final training loss balances these components with weights lambda t equals 1, lambda s equals 0, 1, and lambda sb equals 0, 0, 1. The spatial window size z is set to 2, and the temporal window k is scaled based on the video length. It's important to note that the proximity prior is imposed only during training. At inference, the model scores each patch and segment independently. This allows the system to localize distinct anomalies separately while still benefiting from the smoother, more robust representations learned during training. Evaluation in this domain has been problematic. Most papers report TIOU, which measures the overlap between predicted and ground truth anomaly regions. However, TIOU can be gamed. A model can achieve high TIOU by flagging all frames as anomalous, correctly covering the ground truth, but generating massive numbers of false positives. To address this, the authors adopt track-based detection rate and region-based detection rate, or TBDR and RBDR. RBDR measures the proportion of ground truth anomalous regions detected with sufficient IOU while penalizing false positives per frame. TBDR extends this temporally, requiring that a significant fraction of regions in an anomalous track are correctly detected. This joint metric provides a much more rigorous assessment of spatiotemporal localization capability. The results demonstrate the effectiveness of this approach. On UCF-Crime, the method achieves a TIOU of 40.51, surpassing the previous best by nearly 7.6 percentage points. On Shanghai Tech, it improves by 2.79 points. The gains are even more pronounced on the newly annotated datasets. On UBNormal, the model achieves a TBDR of 57.23% and RBDR of 33.29%, significantly outperforming all baselines. This highlights strong generalization to subtle and small-scale anomalies. Zero-shot evaluation further confirms the model's robustness. When trained without samples from specific anomaly classes, the performance drop is minimal, with a TBDR decrease of only 3.08%. This suggests the model learns generalizable anomaly features rather than overfitting to class-specific patterns. Computational efficiency is also competitive. On a 60-frame input, the model requires 44.23 milliseconds and 6.75 GB of memory, including the shared backbone. This slight overhead is justified by the significant gains in localization accuracy and maintains suitability for real-time inference. Ablation studies validate the design choices. Removing the spatial transformer causes the largest performance drop, reducing TBDR by 19.15 points. This confirms that spatial attention is crucial for precise region-level localization. Removing the temporal transformer also degrades performance, highlighting the importance of modeling temporal dynamics. The proximity-aware mill mechanism contributes a measurable improvement, refining spatiotemporal alignment. The ablation on grid resolution and window size shows that the 7x7 grid with Z equals 2 is the optimal configuration. Coarser grids lose spatial detail, while finer grids introduce noise. The moderate window size captures sufficient context without oversmoothing. The combination of L1 and L2 normalization losses yields the best results, confirming their complementarity in enforcing sparsity and consistency. Finally, a major contribution to the community is the release of frame-level bounding box annotations for the test sets of XD-Violence and UBNormal. Previously, spatial annotations were only available for UCF-Crime and Shanghai Tech. The authors annotated 500 anomalous videos in XD-Violence, resulting in 27,654 labeled frames, and 158 videos in UBNormal, producing 3,388 labeled frames. This enables standardized evaluation of spatial localization on these benchmarks and will facilitate future research in spatially grounded WSVAD. This work moves weekly supervised video anomaly detection beyond purely temporal localization. By reformulating MIL at the patch level and introducing proximity-aware selection, the authors achieve fine-grained spatiotemporal localization without the cost of bounding box supervision. The combination of architectural innovation, rigorous evaluation metrics, and open resources sets a new standard for the field. If you're working on video anomaly detection, this paper is essential reading. The patch-based approach offers a clear path to interpretable models, and the new annotations are a valuable resource for benchmarking. Check the code and annotations in the repository to integrate these techniques into your own research.